There is a world in our solar system where the surface is frozen solid. There are no forests, no oceans are visible from above, and there is no atmosphere that a human could breathe. The sun is too distant to provide any meaningful warmth to the exterior. This view of Jupiter and its moons places this world in its true context, a small point of light orbiting a massive gas giant planet, deep in the cold of the outer solar system. This is Europa. Close-up images reveal a surface scarred by brownish streaks and deep, jagged cracks. Based on this exterior alone, Europa appears to be a dead, irradiated rock where biology cannot survive. Beneath those kilometers of frozen crust lies an enormous, unbroken ocean. This diagram compares the total volume of Earth's oceans to the water on Europa. Despite its small size, this moon holds more liquid water than Earth. It is a planetary-scale ocean, trapped entirely beneath a thick ice shell. We have located the largest body of water in the solar system, but it is locked inside a massive icy vault. Current evidence suggests this water has remained in a liquid state for billions of years. That span of time is what makes NASA's 3 requirements for life so significant. Liquid water is the first requirement, and Europa has it in abundance. The remaining 2 are found at the rocky seafloor, a specific set of chemical elements, and a steady source of energy. Over eons, these 3 ingredients react at the seafloor, maintaining constant chemical exchange beneath the ice. In a pitch-black ocean where no sunlight reaches, the source of energy is less obvious. It comes from tidal heating. As this model shows, Jupiter's gravity physically stretches and squeezes Europa as it orbits, creating internal friction. That friction generates massive heat deep inside the moon, which vents through the rocky seafloor and into the cold water above. This makes Europa unique. It is the only other world we have found where the specific conditions necessary for biology work together in unison. If these conditions are enough to support biology in the dark of the outer solar system, it suggests life may be a common feature of the universe rather than a statistical fluke. Testing that theory is difficult. We cannot land on the surface, drill through the crust, or drop a submarine into the abyss. Instead, we are sending the Europa Clipper. This photograph shows the craft's scale, designed to withstand intense radiation while carrying specialized sensors. The mission will perform repeated flybys, scanning the ice and mapping the hidden ocean from space. This indirect data verifies the interior chemistry of a world we cannot yet touch. The spacecraft will analyze water plumes venting into space and look for the chemical signatures of the ocean water below. We are searching for the point where simple chemistry becomes active biology. Success would prove that the ingredients for life are not unique to the inner solar system. This mission allows us to finally test the evidence and determine if we are truly alone in the dark. When we look out into the outer solar system, past the asteroid belt, the first major landmark is Jupiter and its massive collection of moons. If we pull Europa, one of Jupiter's 4 large Galilean moons, out of that orbit and place it right next to our own moon, you'll see they are roughly the same size. But visually, the 2 worlds have almost nothing in common. Europa's surface is bright, almost entirely white, and covered in a dense network of prominent reddish-brown fractures and ridges. Our moon is a gray, heavily cratered rock that hasn't changed much in eons. Europa's bright, scarred exterior tells us immediately that this ice-covered world operates under a completely different set of physical rules. Like the rest of the major bodies in the solar system, Europa formed billions of years ago. This timeline charts the 4.5 billion years since the moon's creation. Yet NASA estimates the physical surface we see on Europa is extremely young in geological terms, only 40 to 90 million years old. That leaves us with a massive void. Billions of years of geological history are missing from the moon's exterior. Normally, a celestial body that old would be densely covered in craters from an endless barrage of asteroid impacts. Having a brand new geological face means something is actively erasing that history. If a 4-billion-year-old moon has a 40-million-year-old face, the older crust had to go somewhere.
It must be in a constant state of destruction. This topographical image reveals how. We see a chaotic web of ridges and grooves, showing a heavily fractured crust. Notice the intersections. Newer ridges cut directly across older, faded grooves. The ice is constantly breaking apart and paving over older features, a process called resurfacing. This continuous cycle of breaking and refreezing acts as a massive planetary eraser, literally wiping away the craters and the deep history that would otherwise mark the exterior. Those vast lines crisscrossing the moon aren't impact scars from space debris. They are self-inflicted wounds from a violently active, moving crust. Moving and reshaping an entire planetary surface takes a tremendous, continuous supply of energy. As these massive, jagged blocks of the ice shell constantly grind against each other, that physical friction generates and releases intense heat from within. Every new crack, every shifting ridge we observe on the surface is a direct output of this unseen internal engine churning away. Because Europa's exterior is violently tearing itself apart and rebuilding itself, we know with absolute certainty that it contains an active heat source powering that destruction. For a long time, the assumption was that any moon orbiting this far out in the freezing outer solar system would be a static, dead rock. Europa's continuous resurfacing, its shifting ice, and its internal heat generation completely upend that expectation. A surface moving with this much heat and mechanical energy simply cannot be anchored to a solid block of ice stretching all the way down to a rocky core. There has to be a buffer layer allowing that movement to happen. Europa is a dynamic system, a world governed by powerful internal forces rather than a passive frozen wasteland. That leaves us staring at the boundary between the broken ice we can photograph and the heated interior we can't see. To continually break apart a planetary ice shell and overwrite its surface, something massive has to be physically displacing that ice from underneath. The young, constantly shifting crust is proof that somewhere beneath the ice, something enormous is moving.
On the surface, Europa is a frozen, fractured wasteland. But beneath that scarred exterior lies a massive liquid water ocean, a world that might harbor the ingredients for life. Between us and that water sits a massive physical barrier, tens of kilometers of solid, densely packed ice. Because of that immense thickness, we cannot capture a standard Hollywood-style photograph of the ocean hidden below. Since visible light cannot penetrate the shell, exploring Europa's depths requires an entirely different method of observation. The Europa Clipper spacecraft is the platform designed to carry out this exploration. On board is a specialized instrument called REASON, short for Radar for Europa Assessment and Sounding, Ocean to Near Surface. REASON avoids the limitations of visible light by using radio waves, long wavelength signals that can pass through solid materials that would block a standard camera. It is a tool designed to probe the ice's internal structure using pulses of electromagnetic energy. The principle is surprisingly simple. The instrument fires radio waves straight down into the moon's surface. Under favorable conditions, NASA expects these waves to travel tens of kilometers deep into the frozen shell. While some energy dissipates, a portion of the waves will strike solid boundaries or changes in material and bounce back up toward the spacecraft. This return trip provides the mechanism for retrieving structural data from deep within the moon's interior. This data plot shows the timing of the returning signal. By measuring exactly how long the echo took to return, scientists determined the precise depth of the object the wave hit. The specific characteristics of the waveform, its shape and strength, act as a unique signature for the type of material it encountered. By analyzing these reflections, scientists can reconstruct internal structures, mapping out distinct ice layers and potential pockets of liquid water. They can identify sudden material boundaries and trace potential pathways that might connect different environments beneath the surface. This translation process allows for the construction of a comprehensive three-dimensional map, using nothing but invisible echoes. The final product of the REASON instrument is a deep, penetrating structural map, fundamentally different from a standard surface photograph. It functions much like a medical CT scan, allowing humanity to effectively X-ray the interior of an alien moon for the first time.
Mapping this internal anatomy is the essential first step toward determining if Europa harbors the conditions necessary for life. But the mission's observations extend beyond the subterranean. The RE instrument on the Europa Clipper is also designed to look outward, actively monitoring the space environment surrounding the Moon. This dual perspective provides a comprehensive look at both the Moon's internal structure and its external surroundings. Out in the dark outer reaches of our solar system, Jupiter's moon Europa holds more liquid water than all of Earth's oceans combined. That massive volume makes it a premier location to search for life, but there is a major problem with accessing it. That vast body of water is trapped beneath a rigid shell consisting of miles of dense ice. Looking at the deep scars and cracks across the moon's exterior, you can see just how thick and unforgiving this frozen barrier really is. On Earth, if we want to study a deep subterranean lake, we bring heavy equipment to cut through the rock. But sending a mechanical drill or an automated submarine hundreds of millions of miles through space to cut through a frozen crust is currently beyond our engineering limits. This leaves us with a difficult problem. How do you measure the chemical properties of an ocean that you cannot reach, touch, or even see? Unlocking Europa requires a different approach, analyzing the environment from orbit to reconstruct the chemistry hidden miles below the surface. Fortunately, that massive ice shell is not perfectly watertight. The constant stress and shifting of the crust allows microscopic amounts of water and gas to seep upward through the deep fractures, eventually escaping into the vacuum of space. This leak alters the entire exploration strategy. Rather than designing a mission that forces its way down to the water, the spacecraft is designed to let the water come up to it. Determining if this ocean is habitable doesn't require a physical submarine. It requires highly sensitive instruments capable of capturing the microscopic chemical whispers floating just above the moon. That is exactly what an instrument called MASSPEX is built to do. It is a highly specialized mass spectrometer designed to sweep through Europa's thin atmosphere and pull in whatever trace gases it encounters. The ideal scenario is that Europa is actively venting geysers into space. If there are active plumes erupting from the surface, MASSPEX can fly the spacecraft directly through the exhaust cloud to collect a dense sample. Inside, MASSPEX sorts the chaos. It charges molecules and uses a magnetic field to weigh them, revealing exact chemical signatures for compounds like water or methane. Because radiation blasts them apart, scientists mathematically reverse this decay to reconstruct the original pristine chemical structure. Once they know exactly what the chemical is, the final variable to solve is location. They have to trace the orbital trajectory to find exactly which crack or ridge on the moon's surface expelled it. By locking down those three variables, the specific chemical identity, the rate of radiation decay, and the physical point of origin, the team can accurately map the chemical makeup of an ocean they can't even see. But relying on active geysers is a gamble. If Europa happens to be quiet during the flybys and no plumes are erupting, the mission needs a backup plan. That backup plan is the Surface Dust Analyzer, or SUDA. Even without active geysers, space is filled with microscopic debris constantly striking Europa's icy plains, blasting tiny fragments of the solid surface upward. These continuous impacts create a thin, permanent haze of solid dust around the moon. SUDA operates like a high-speed catcher's mitt, flying through this haze and scooping up the ejected particles directly out of orbit. This image highlights the highly detailed, mineral-rich ridges across Europa's exterior. By capturing even a single microscopic speck of dust thrown from these formations, SUDA provides a physical sample of the crust itself. With this tool on board, the moon doesn't have to actively vent a massive geyser. The surface is continuously offering up samples, piece by microscopic piece. When scientists combine the atmospheric gas readings from MASSPEX with the solid dust analysis from SUDA, they get two completely distinct sets of data that verify one another. Together, they create a comprehensive chemical map of the moon. Every particle captured by these instruments serves as a physical link between the vacuum of space and the moon's interior. By charting exactly where the spacecraft caught it in orbit, scientists can trace its path back to the surface, through the deep ice fractures and all the way to the water below. For the first time, we can determine if a world is habitable without ever touching a drop of its water. Achieving this requires massive facilities, sprawling cleanrooms, and heavy engineering, all dedicated to capturing targets literally invisible to the naked eye. We cannot force our way into Europa, but by patiently flying through the dark and intercepting the chemical whispers left behind, we can finally learn exactly what is hiding in the water.
Welcome to this explainer. Today, we're jumping right into Chapter 3, The Ocean That Should Not Be There. We're going to examine one of the most mind-bending mysteries in our entire solar system, Europa, an icy moon orbiting Jupiter that's hiding a massive cosmic secret.
To really wrap our heads around this, I want you to start by just visualizing our own familiar planet. Think about the oceans, the continents, everything that makes Earth, well, Earth.
Now strip all of that away. Erase the landmarks, the land masses, the atmosphere, all the life you recognize. You're left with this completely alien, desolate landscape.
And then, picture taking a massive ocean and sealing it entirely beneath a thick, heavy shell of ice. That right there is the basic mystery of Europa. It's a cosmic detective story where a massive body of water is, by all outward appearances, completely hidden from view.
Okay, let's dive into Section 1, Deeper Than Earth. We are talking about a truly massive scale here.
So, the suspected ice shell protecting Europa? It's estimated to be roughly 15 to 25 kilometers thick. That is a massive wall of solid ice. But beneath that, there may be an ocean approximately 60 to 150 kilometers deep. To put that into perspective, that means Europa's ocean could be dramatically deeper than Earth's oceans. And since Europa is much smaller than Earth, the proportion of its interior occupied by water is just absolutely enormous.
Which brings us to this incredible number, 2. Based on these estimates, NASA calculates that Europa's hidden ocean may contain more than twice the amount of water found in Earth's entire global ocean. Literally all the water on our blue planet doubled and shoved inside a moon of Jupiter. No way, right? It's almost hard to wrap your head around.
So let's move to Section 2, the magnetic clue. The crucial point here is, how do we actually know this water is there?
Scientists haven't exactly drilled a hole to look inside. The ocean is inferred from multiple lines of evidence, and one of the most important clues came from NASA's Galileo spacecraft. Galileo repeatedly flew past Europa, and it carried an instrument called a magnetometer, which it used to detect magnetic signatures.
Now, what's really interesting about this is the logical progression. When Galileo flew past, that magnetometer detected a very specific magnetic signature. That signature indicated a conducting layer deep inside the moon. And the most likely explanation for a conducting layer like that? A global salty ocean. So, scientists weren't simply guessing, they were reading Europa's exact response to Jupiter's intense magnetic environment.
Let's transition to Section 3, a frozen lid, and look at the physical clues on the surface.
When you observe Europa's surface, you see these huge fractures and ridges. The way they're arranged actually suggests that Europa's outer shell can move independently of its interior, and that makes perfect sense if, and really only if, a fluid ocean is physically separating that hard ice shell from the rocky interior beneath it.
And this brilliantly illustrates the mechanics of the moon. As the quote says, the surface behaves like a frozen lid floating over something deeper. It's a perfect analogy. The ice isn't anchored down. It's a dynamic floating crust, shifting on a massive buffer of dark, salty water.
Which brings us to Section 4, the lingering question regarding Europa's energy source.
Because proving that an ocean exists where it seemingly shouldn't immediately unlocks an even more profound puzzle. Space is freezing. Europa is incredibly far from the warmth of the sun, so if there is a global ocean containing twice the water of Earth, hidden beneath miles of ice, what keeps the ocean liquid? What is providing the energy? That is the lingering question we are left with. Thanks for joining me for this explainer, and keep questioning what lies beneath the surface.
Welcome to today's explainer. We're going to be unpacking a totally fascinating cosmic mystery right here in our very own solar system. You know, for the longest time, Europa, that's one of Jupiter's moons, well, it was viewed as just this dead, frozen wasteland. But it turns out, beneath that icy shell lies a huge hidden ocean. And today, we're diving into the exact mechanics that actually make that possible. So right off the bat, we run into this massive paradox. At Europa's distance from the sun, we're talking hundreds of millions of miles away. Any water should absolutely be frozen solid. I mean, the temperatures out there in the Jovian system are just unimaginably cold. The ice on Europa's surface, it's literally as hard as granite is right here on Earth. By all accounts, just based on its location in the dark, freezing vacuum of space, this moon really should just be a massive, completely frozen block of ice. through and through. So where does the heat come from? If we know there's a vast liquid ocean sloshing around beneath miles of thick ice, there just has to be an energy source, right? Something incredibly powerful is keeping that water in a liquid state, basically preventing the entire moon from freezing completely solid all the way down to its core. Without the warmth of a nearby star to melt the ice, we are essentially left with a massive planetary whodunit. Well, the answer is Jupiter. It's right next door. Our primary suspect here isn't a star, it's not solar radiation, and there's no greenhouse effect going on. The warmth that's keeping Europa's ocean liquid comes directly from the giant planet it orbits. But wait, Jupiter is a gas giant, right? It's not a burning star. It really doesn't emit the kind of radiant heat that could thaw a moon from hundreds of thousands of miles away. More specifically, gravity. Yeah, pure, invisible mechanical force. This is where the physics of our solar system just become incredibly elegant. See, it isn't light or thermal radiation bridging the gap between Jupiter and Europa. Nope. It is the raw, relentless pull of gravity, acting as a physical force directly on the moon's structure. Part 1. The gravitational engine. So Europa's orbit around Jupiter isn't perfectly circular, it's actually elliptical. And what that means is that as Europa travels along its orbital path, its distance from Jupiter is constantly changing. Sometimes it gets pulled really close to the gas giant, and other times it swings much further away. And because that distance fluctuates, well, the strength of the gravitational pull on the moon fluctuates right along with it. As Europa moves closer to the giant planet, Jupiter's massive gravitational pull literally stretches the moon, like the solid rock and ice are physically pulled out of shape. Then, as Europa swings further away in its orbit, that pull kind of relaxes, and the moon squeezes back inward. So Jupiter's enormous pull stretches the moon. Jupiter's pull squeezes the moon. Again, and again, and again. Every single time it orbits. This rhythmic, mechanical squeezing is happening to the solid rock deep within the moon's core. And scientists have a name for this. It's called tidal flexing. That's the repeated deformation of a celestial body caused by gravitational stress, which generates internal heat. So just like rubbing your hands together creates friction and warmth, this constant planetary scale massage generates massive amounts of internal heat deep within the moon itself. Okay, picture this. Step 1, bend a metal paperclip repeatedly back and forth. Step 2, eventually it heats up, right? If you touch the crease where it's bending, you can actually feel the warmth. The kinetic energy of your movement is being converted into thermal energy through internal friction. Step 3, Europa experiences this exact same thing but on a massive planetary scale. Jupiter is basically the hand bending the paperclip, and Europa's rocky interior is the metal getting hot. The result of all that gravitational stress generating internal heat is pretty profound. That heat radiates outward from the rocky core of the moon and literally melts the underside of the outer ice shell. So that heat can help maintain liquid water beneath the ice. This mechanical heat engine, driven purely by gravity, is the perfect, elegant solution to our frozen water problem. It completely bypasses the need for a warm sun. Part 2, a world without sunlight. And suddenly, the story gets so much more interesting because Europa doesn't necessarily need sunlight to maintain an environment that could be habitable. I mean, for decades, whenever we looked for places where life could exist, we exclusively looked for planets in the Goldilocks zone. Exactly the right distance from a star to be warmed by its light. But Europa completely shatters our standard assumptions. It proves that the energy required for a dynamic, potentially life-supporting environment can actually come from within. To truly grasp why this matters, let's contrast this with our own planet. Look at Earth's surface. Almost all ecosystems ultimately depend on sunlight. Plants use photosynthesis, animals eat the plants, the whole food web relies on solar energy. But look at Earth's deep oceans. We discovered something entirely different down there. Miles below where any sunlight can reach, we've found thriving ecosystems clustered around hydrothermal vents, basically superheated geysers on the ocean floor powered by Earth's internal heat. Life there just thrives in total, absolute darkness. Which brings us to the ultimate question, the one that makes studying Europa so unbelievably thrilling. If complex ecosystems can thrive in the dark of our own oceans, what else might be hiding in the dark waters of Europa? The heat is there, the icy shield is there. The rest, well, it's just waiting to be discovered. Thanks so much for joining me for this explainer. Keep asking questions and keep looking up. Okay, let's dive right in. Welcome to this explainer. Today, we are unpacking a truly profound discovery, one that fundamentally changed our entire understanding of biology and really our place in the cosmos. We're going to explore the Europa thesis, chemical engines of life, and see how the hidden secrets of our own world might actually unlock the mysteries of another.
So let's start with the 1977 paradigm shift, shattering some massive assumptions down in the deep.
Because to really understand Europa, we have to start right here at home. The year is 1977. I want you to anchor this year in your mind because it marks a definitive before and after moment in science. Researchers made a shocking discovery that basically took all the established rules of biology as we knew them and threw them right out the window.
Deep beneath Earth's oceans, scientists discovered hydrothermal vents. And these vents were absolutely teeming with life. But here's the crazy part. There was no sunlight down there whatsoever. Absolute darkness. And yet, entire ecosystems existed and thrived. This completely shattered the long-held assumption that the sun is a hard, non-negotiable requirement for life.
Which brings us to a completely new engine for life, surviving in the dark. This totally rewrote the rulebook. We used to think the old rule was absolute. Life needs sunlight. But the new rule? Life simply needs energy. That discovery changed how scientists thought about life forever. Life didn't necessarily need a star to survive. It just required an energy source. And man, that matters enormously for Europa. So how do they do it? The answer is a process called chemosynthesis. Basically, microorganisms can obtain energy from chemical reactions associated with the interaction between seawater and a hot, rocky environment. This is the exact mechanism these deep-sea microbes use to fuel their sunless ecosystems. They are, quite literally, chemical engines. All right, let's look at the case for Europa, projecting these earthly discoveries out into deep space. This earthly paradigm matters so much for our search for life beyond Earth, because beneath Europa's thick, icy crust, there's likely a rocky ocean floor, and thanks to the immense gravitational pull of Jupiter, there's the potential for tidal heating actively warming that rocky interior. These are the exact physical conditions that make Europa such a prime candidate for hosting biological ecosystems, entirely hidden from the sun. Let's walk through how this builds into a functioning chemical engine. Step 1. Tidal heating warms that rocky interior. Because of that heat, Step 2, water could interact with the rock. That interaction means, Step 3, chemical gradients could form, making hydrogen and other vital compounds available. Which leads us to Step 4. In principle, some of the chemistry needed to power microbial life could exist right there in the dark oceans of Europa. And you know, this isn't just speculation. NASA specifically identifies water-rock interactions and possible hydrothermal systems as potential sources of chemical energy on Europa. This officially grounds these theoretical steps in authoritative, cutting-edge space science. The exact same mechanism we found at the bottom of our oceans in 1977 might be operating right now beneath Europa's ice. But let's look at possibility versus observation and really ground the science here. Because before we get too carried away, we need a rigorous scientific reality check. There is a problem, a major one. We don't actually know whether Europa has hydrothermal vents. We have the models, we have the theory, but we are missing a massive puzzle piece. Right now, these vents are a possibility, not an observation, and that distinction matters deeply. Theoretical models and potential conditions are entirely different from what has actually been confirmed and seen. Separating what could theoretically exist from what we've actually confirmed is the absolute bedrock of the scientific method. As the source material so perfectly puts it, this documentary isn't about inventing monsters underneath the ice. It is about following the evidence as far as the evidence allows. And that is our absolute commitment in this explainer too. We're prioritizing strict scientific rigor over science fiction hype. We aren't inventing aliens, we are simply following the chemical and physical evidence step by step, right to the very edge of what we currently know. So I'll leave you with this final provocative thought to take away from this explainer. If we strictly follow the evidence, what might eventually be revealed in the dark oceans of Europa? We have already seen how life finds a way in the pitch black of our own world using chemical engines. We know the ingredients might be waiting beneath that alien ice. The evidence is clearly pointing us toward the dark. Now, we just have to go look. Welcome to this explainer. Today, we're basically playing cosmic detectives.
You see, when scientists look out into the deep, freezing expanse of our solar system, they aren't just looking at random rocks and ice, right? They're actively hunting for a very specific recipe. They want to know if the fundamental ingredients for life exist out there, beyond our home planet. And right now, well, Jupiter's icy moon Europa is absolutely front and center in this investigation.
Which brings us to the ultimate question. So what would life actually need? I mean, if we're going to search the cosmos for extraterrestrial life, we first have to ask ourselves what the baseline requirements are. If you strip away all the wild complexity of life here on Earth, the forests, the animals, us, what are the absolute bare minimum requirements for biology to even have a chance of taking hold?
To figure that out, we're going to look at the evidence in 5 quick steps. Number 1, the recipe for life. Number 2, ingredient 1, water. Number 3, ingredient 2, chemistry. Number 4, ingredient 3, energy. And finally, number 5, an interconnected system. All right, let's jump right into part 1, the recipe for life. At the simplest level, scientists are generally looking for 3 major ingredients: water, chemistry, and energy. It's a deceptively simple list, isn't it? But finding all 3 of these together in one place, especially in the harsh environment of deep space, is incredibly difficult. You basically need a liquid solvent, you need chemical building blocks, and you need a power source to make the whole shebang run. So moving on to part 2, let's talk about ingredient 1, water. Now, Europa, we can confidently check off this first box. Liquid water is present on Europa, so it appears to have the very first ingredient. And just to be clear, we aren't just talking about solid ice here. We're talking about actual liquid water sloshing around beneath its thick, frozen shell. When you're looking for life as we know it, finding liquid water is quite literally step 1 in the investigation. That brings us to part 3, ingredient 2, chemistry. So you've got the water, but what are the raw materials mixing around in it? The chemical elements associated with life as we know it include carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. You can kind of think of these 6 elements as the essential cosmic Legos. They're the basic chemical foundation that biology uses to build up all those complex structures. Without these specific elements, the recipe simply doesn't work. And here's the good news for our cosmic detectives. There is actually evidence that at least some relevant chemistry exists on Europa. So it may indeed have this second ingredient. It's not just a sterile, empty ocean of water. The building blocks, those vital Lego pieces we just listed, seem to be there. And that makes that hidden subsurface ocean potentially very interesting, chemically speaking. Okay, part 4, ingredient 3, energy. On Europa, we actually have 2 incredibly fascinating potential sources of energy at play. On the inside, we have tidal heating driven by gravity. Basically, as Europa orbits Jupiter, the massive gravitational pull stretches and squishes the moon, which generates heat from within. But then, on the outside, we have Jupiter's intense radiation, and this exterior radiation provides another completely different but highly interesting piece of the puzzle. Let's actually trace this chain reaction because it's pretty wild to see how that exterior radiation could power an ocean hidden beneath miles of ice. So, step 1. Jupiter's intense radiation constantly bombards Europa's icy surface. Step 2. This physically breaks apart the molecules sitting there on the ice. Step 3. That resulting chemistry creates compounds known as oxidants. Now, step 4, if some of those newly created oxidants could eventually be transported down into the ocean below, well, step 5, they could potentially participate in chemical reactions that actually release energy. It's this incredible potential mechanism for delivering power from the frozen dead surface straight down into the dark ocean.
Which leads us perfectly into part 5, an interconnected system.
So, based on what we've learned, Europa could have a highly unusual system at work. If we start from the very top, the surface is being chemically altered by radiation. The moon is taking a constant heavy beating from Jupiter, which is actively changing the chemistry of its icy shell. But contrast that with the deep interior. While the outside is being bombarded, the interior is being heated by gravity. The immense gravitational tidal forces from Jupiter are physically churning and warming the inside of the moon. And sandwiched perfectly in the middle of these 2 extremes is our crucial first ingredient. The liquid water ocean sits between the frozen, radiation-altered ice above and the warm, gravity-heated rock below.
Now, what makes this so incredibly compelling is that these layers aren't strictly isolated from one another. Materials may actually move between these environments. The oxidants from the irradiated surface might cycle down, and warm materials from the rocky seafloor might cycle up. It's a dynamic, moving environment where the ingredients for life actually have the opportunity to mix.
And that brings us to the most important takeaway of this explainer. To quote directly from the source material, that is exactly the kind of interconnected system scientists want to investigate. It's not just that Europa has water or chemistry or energy sitting in isolation. It's that it appears to have all three operating in a single, complex machine where they can interact. It is literally the perfect cosmic kitchen.
The ingredients are there, the system is dynamic, and the case for exploring Europa is incredibly strong based on this recipe alone. But again, to quote the researchers, but then something happened that made Europa even more interesting. I mean, what could possibly make this icy alien ocean even more tantalizing to scientists than it already is? Well, that is a mystery we'll just have to leave you pondering for today. Welcome to The Explainer. Today, we're pointing our lens at one of the most fascinating and frankly mysterious objects in our entire solar system. I'm talking about Jupiter's icy moon, Europa. Now, we've known for a while that Europa likely harbors a massive liquid ocean, tucked way down deep beneath its frozen, scarred crust. But the big question, the ultimate question really, has always been how on Earth, or how in space, do we actually get to that ocean? Well, there's a tantalizing mystery right now that might just give us the ultimate shortcut. We're diving into a real-life scientific detective story today, and it's a puzzle that's kept planetary scientists on the absolute edge of their seats for years.
Okay, let's dive right into this, because to really understand this mystery, we've got to focus on one specific word here: controversial. You see, in the quiet, super rigorous, data-driven halls of planetary science, a controversy usually means we're standing right on the edge of a massive breakthrough, or, well, a frustrating misunderstanding. And Europa? Europa has given us a clue that sits perfectly on that knife's edge, absolutely demanding our attention.
Part 1. Europa's most controversial clue.
So, what is this clue? Plumes. And the sheer mind-boggling scale of what we're talking about here is just amazing. In planetary science, plumes are essentially these giant cosmic geysers. Basically, scientists have reported evidence suggesting that water vapor might occasionally escape from Europa's icy shell, just bursting right out into the vacuum of space. If this is true, it means Europa isn't just, quietly holding on to its subsurface ocean. It's actively venting it out into the solar system. Now, that first massive wave of excitement, that came straight from the legendary Hubble Space Telescope. It turned its gaze toward Europa and actually produced evidence that was totally consistent with water vapor hovering right above the moon's surface. And it wasn't just a fleeting one-time glitch either. Over the years, later observations and analysis have kept investigating this possible plume activity, desperately looking for that smoking gun. I mean, it's an incredible thought, right? Alien water blasting hundreds of miles high into space. But, well, as is usually the case when we're chasing the truth, there is a complication.
Which brings us to part 2, reality versus internet sensationalism. I'm sure you've seen the videos online. You know the ones. Bright thumbnails, all caps, flashing text screaming, NASA found water erupting from Europa. It sounds incredibly definitive, doesn't it? Like we've got 4K video of a cosmic water park. But actually, scratch that. That statement is just way too confident. Let's slow down a sec and look at what NASA itself, the very agency doing the research, has actually stated. They firmly emphasize that Europa's plume evidence is intriguing rather than definitive. In science speak, intriguing means keep looking, we might be onto something. It definitely does not mean case closed. Space is incredibly tough, the data is noisy, and false positives are a real, constant threat to researchers.
So yeah, the actual scientific story is a lot more complicated. There are absolutely observations out there that are consistent with plumes. The math works out, the physics makes sense, but researchers want stronger, undeniable evidence before they go rewriting the textbooks and declaring a definitive discovery. They need a lot more than just faint spectral signatures from a telescope sitting in Earth's orbit. They need to get up close and personal with this icy moon.
Part 3. Sampling oceans without landing.
Now here is the absolute best part about all this. It's about what we do not have to do if these plumes actually exist. Think about the absolute nightmare logistics of trying to sample an alien ocean. First, you'd have to figure out how to land safely on an unknown, jagged, highly irradiated surface.
Then you'd have to deploy some kind of massive drill to cut through miles, literally kilometers, of rock-hard, freezing ice. And then you'd have to somehow reach the ocean directly without your gear breaking or contaminating the pristine water. That's an engineering hurdle that honestly borders on pure science fiction right now. But if the plumes are real, we can cross out every single one of those grueling steps.
Because if Europa really does send material from its subsurface environment straight into space, the solution becomes incredibly elegant. We just fly through the vicinity and we collect the molecules. Imagine that for a second. Just picture a spacecraft coasting silently through the cold void of the Jupiter system, opening up its specialized sensors and gracefully catching pristine droplets of an alien ocean without ever touching the ice below. It is literally the ultimate cosmic free sample.
And that amazing potential is one of the massive reasons NASA's Europa Clipper mission exists. This isn't just some casual sightseeing tour of the outer solar system. No way. It's a highly calculated, ambitious interception mission. Clipper is designed to swoop past Europa dozens of times, carrying these incredibly sensitive instruments that can practically sniff the environment around the moon. It's hunting for those exact plumes. It's looking for the definitive truth behind those controversial clues Hubble gave us all those years ago.
Which leaves us with this final, thrilling question to ponder for today's explainer. If Europa's hidden ocean is already venting into space, if that water is already out there waiting for us in the dark, what molecular secrets will the Clipper catch as it flies through? We are right on the precipice of finding out. Thank you so much for exploring this with me today, and as always, keep looking up.
All right, let's jump right into this one. Welcome back. In this explainer, we are unpacking one of the absolute coolest celestial detective stories of our time. We're looking at Europa, which is one of Jupiter's icy moons and the ultimate mystery it presents. Because look, we know there's a massive alien ocean hiding under there, but how do we actually look inside it? It's a puzzle that has kept planetary scientists up at night for decades. Getting to that water, that is a totally different story. So let's look at the clues we finally have.
You see, this brilliantly illustrates our central challenge. How exactly do you study an ocean that is locked away beneath kilometers of rock-hard, freezing ice? For the longest time, everyone just assumed that to know what was in that alien ocean, we'd literally have to land on the surface, bring some kind of incredibly massive futuristic drill, and bore through miles of crust just to hit water. It's a total engineering nightmare. But as you'll see, nature might have just handed us a spectacular workaround.
So let's get right into Section 1, the James Webb discovery and a breakthrough in Terra Regio.
Okay, so the year is 2023. This is exactly where the story shifts from theoretical guesswork into concrete data. This is when NASA pointed the James Webb Space Telescope, which, by the way, is the most powerful observatory we've ever put into space, right at Europa. And we weren't just taking pretty pictures here. We were conducting a deep chemical analysis of the moon's surface from roughly 1 million miles away.
And here is the specific, groundbreaking finding they got back. The data showed carbon dioxide. But it wasn't just everywhere, it was heavily concentrated in a very specific geographic area of the moon known as Terra Regio. Now, if you're a planetary scientist, finding concentrated carbon dioxide on a frozen moon is basically a huge flashing red alert. It means something complex is happening. But, as always in this field, we have to follow the logic really carefully.
Which brings us to Section 2, the origin of the clue. Specifically, where did it come from?
Because look, finding carbon dioxide alone absolutely does not mean we found biology or life. Carbon dioxide is honestly pretty common in the universe, and it can easily form without any biological processes whatsoever. So just seeing the gas is really only the first breadcrumb in our mystery. The absolutely crucial question is this: where did this carbon actually come from? Tracking down its origin point on Europa was the single most important next step, because it wasn't just scattered randomly, it was concentrated in Terra Regio. The location itself became the key to solving the puzzle.
Scientists basically had two major theories to wrestle with here. Was this carbon just delivered to the surface by meteorites crashing into the moon over billions of years? Or did it actually well up from Europa's own subsurface ocean? Well, the telescope data was a total game changer. By analyzing the concentration and the specific location, the data strongly indicated that the carbon likely originated from Europa's subsurface ocean, rather than being delivered from space by meteorites. I mean, that is a massive revelation. It means material from that hidden underground environment has literally reached the surface.
And that leads perfectly into Section 3, a window to the ocean, and solving the drilling problem.
Just think about this quote for a second.
Scientists may not have to drill through kilometers of ice to study every part of Europa's interior. I mean, think about what that actually means for us. The moon itself might actively be bringing the clues upward. Nature has essentially provided an incredibly elegant solution to an impossible engineering problem. We don't need to build a sci-fi megadrill. The ocean is delivering its secrets directly to the surface.
Let's walk through the mechanics of how this works because it's fascinating. Think of it like a cosmic elevator. Step 1, it starts deep down in the liquid ocean. Step 2, it pushes up into the thick ice crust. Step 3, it breaks through to the visible surface. And finally, Step 4, it sits there exposed to space, where our telescopes can actually see it. Europa isn't just some dead, locked vault. It's a dynamic, churning world where the deep down directly connects to the high up above.
And this vertical movement creates a possibility that is just incredibly important for future space missions. If the ocean contains really interesting chemistry, the kind we desperately want to study, some traces of that chemistry might become fully accessible from above. We can literally study the dark depths of an alien ocean just by orbiting the moon and looking closely at its surface. It completely rewrites the playbook for how we explore Europa moving forward.
But we do need to take a step back for Section 4, Habitable versus Inhabited, the reality check.
Okay, it is time for a sobering reality check on what this 2023 discovery actually proves, and more importantly, what it definitely doesn't prove about alien life. Let's rapid fire through some vital caveats because being scientifically accurate here is crucial. First, carbon is not life. It's a building block for sure, but it is not a living organism. Second, even complex organic molecules are not automatically life. And third, even if we end up finding a massive soup of life's ingredients on Europa's surface, that still doesn't prove biology is at work. There is an immense, massive gap between having the chemical building blocks and actually having living, swimming organisms.
So what you really need to take away from this entire explainer is one critical distinction. We have habitable, which simply means an environment is structurally and chemically capable of supporting life, versus inhabited, which means the environment is currently hosting actual biology. Understanding the difference between a habitable world and an inhabited world is arguably the most important idea in the entire Europa story. We are finding profound evidence that Europa might be highly habitable. But inhabited? Well, that's a prize we just haven't claimed yet. Which leaves us with a pretty thrilling final question to ponder. Since we now know we likely don't have to drill to access the ocean's secrets, what exact chemical signatures will future missions need to look for on that icy surface to finally cross the line and prove Europa is actually inhabited? We have the clues, we have the location, and we now have the means to look. The next chapter of this mystery is going to be absolutely incredible. Thanks for joining me on this explainer, and keep your eyes on the stars. Welcome to another explainer. Okay, let's dive into this. Today we're unpacking Chapter 09, The Machine Going There. We are looking directly at the sheer mind-bending logistics of the Europa Clipper mission. We know what it's looking for, but the actual mechanics of getting this machine to its destination and keeping it alive once it's there, it's an absolute masterclass in orbital strategy.
2.9 billion kilometers. Yeah, that is the staggering distance this spacecraft is traversing. It's traveling roughly 2.9 billion kilometers toward Jupiter. Honestly, it's kind of difficult to even wrap our human minds around a number that vast, but that is the reality of the immense, silent void this machine is crossing literally right now.
Section 1. An epic journey begins.
So to truly understand how we're bridging that incomprehensible gap, we need to look at the timeline. The journey officially began on October 14, 2024. That's when the Europa Clipper launched and successfully escaped Earth's gravity. Right now, it's in the middle of a massive deep space transit. It's going to take 6 full years of coasting and adjusting through the dark before it reaches its destination. It is scheduled to finally arrive at the Jupiter system in 2030. That's 6 years of travel just to get to the starting line of the actual science.
The radiation problem. Now, what's really interesting about this slide is the massive hurdle the mission faces the second it arrives.
Because arriving is really only half the battle. Once it reaches the Jupiter system, it begs a very logical question: why not simply orbit Europa? I mean, if Europa is our ultimate target, the whole reason we spent 6 years traveling 2.9 billion kilometers, why not just park the spacecraft right next to it and stay there? Well, the answer comes down to pure, brutal survivability. To orbit Europa directly would expose the spacecraft to an intense radiation environment. Jupiter's magnetic field is an absolute monster, and it traps and accelerates particles to incredibly high speeds. Orbiting Europa directly would constantly bathe the spacecraft in this deadly radiation, effectively cooking the electronics and destroying the machine way before it could complete its work.
Which brings us to the flyby solution. So, if you can't stay at Europa, how do you study it? NASA's engineers had to get incredibly creative to keep this highly sensitive machine safe. Instead of going for an orbit around Europa, which guarantees intense radiation exposure, the Clipper will orbit Jupiter itself. By taking a much wider, highly elliptical path around the gas giant, the spacecraft can swoop in to perform repeated close flybys of Europa. It basically dives in, gathers data, and then immediately sweeps back out into safer, much less irradiated space to cool down and transmit everything back to Earth.
NASA's current mission plan calls for exactly 49 close flybys. That's 49 highly precise, carefully choreographed swoops right through the danger zone. It's a calculated orbital dance designed to perfectly balance extreme risk with the ultimate scientific reward.
Piecing together the puzzle.
So how do we make the absolute most out of these incredibly brief, high-speed encounters? How do you map a world when you're essentially doing drive-by science? Well, each pass becomes another piece of the puzzle. During every single flyby, the Clipper will map a different segment, scan a different region, and systematically build a comprehensive picture of the icy moon over the course of several years.
The Planetary Investigation Team. Let's move to and see how this builds, because this scientific payload is basically an elite detective squad. To gather all of those puzzle pieces quickly during those high-speed passes, the Clipper is carrying some incredible gear. Each tool has a highly specialized job to do the second they get close to the moon. First up, we have an instrument that examines the surface. It's looking directly at the ice, searching for fractures and geological clues.
While that's happening, another instrument studies the magnetic environment. This is absolutely critical for understanding how the ocean behaves deep beneath that icy crust.
At the exact same time, a third instrument investigates gases. It's essentially sniffing the immediate environment to see what's being vented out into space.
Next, we have an instrument that studies dust. By capturing and analyzing these tiny particles, the spacecraft can learn a ton about Europa's composition.
Then there's the radar. Another instrument uses radar to probe beneath the ice. This allows us to literally look under Europa's frozen shell and determine its thickness, peering straight into the dark.
And rounding out this rapid-fire crew, another instrument measures thermal signatures. It scans for warmer patches, giving us a heat map of the moon's surface activity.
And this brilliantly illustrates the true genius of the Europa Clipper. It isn't just one camera taking pictures. Together, they create something like a planetary investigation team. All of these separate, highly specialized instruments work in perfect synchronization, checking each other's findings during every single one of those 49 high-stakes flybys.
But, within this elite team of scientific tools, there's a hierarchy. While every single instrument plays a vital role in piecing together this massive puzzle, one instrument is particularly important. Out of all the high-tech gear on board, there is a single key player that this entire mission truly hinges on. What is it? Well, you're going to have to stick around, because we will uncover exactly what that crown jewel is in our next explainer.
All right, let's dive right in. Welcome back, everyone, to another explainer where we take some seriously complex research and break it down into the core concepts you actually need to know. Today, we're exploring a massive, literally mind-bending paradigm shift in space exploration. We're looking directly at the incredible insights from Chapter 12 of Deep Secrets. If you love cutting through all the noise to get to the structural truths of science, well, you're in the perfect place. We're going to completely rethink what it means to search for a habitable ocean out there in the dark stretches of our solar system, especially when we talk about icy moons like Europa or Enceladus.
So, for the longest time, whenever we looked at icy moons or distant worlds through our telescopes, we were all basically trained to look for one ultimate finish line. The driving question behind almost every single planetary mission was simply, is there an ocean? It seemed like the absolute holy grail of astrobiology, right? The logic was super simple. If we found water, we won. Mission accomplished. But astrobiologists have realized a profound secret. That is completely the old way of thinking. Finding that water, it isn't the finish line at all. In fact, we kind of have to toss that old framework completely out the window.
Now, what's really interesting about this pivot in scientific thinking is just how striking it is. The old question, as we said, was simply, is there an ocean? We've actually already answered that for several distant worlds, so check.
we can cross that right off the list. The new, much bigger, and infinitely more complex question is, what is the ocean like? The realization here is that finding an ocean is just the absolute bare minimum starting point. The real work, the true mystery, kicks off the exact second we confirm that water actually exists.
And this pivot? It brings a barrage of completely new, incredibly specific structural mysteries that scientists now have to solve. First off, is it extremely salty? And this isn't just about taste, obviously. The salinity and the chemical makeup of the water dictate absolutely everything about the physical reactions that can or cannot happen within that alien environment.
Then we immediately have to ask the next big physical property question: how deep is it? I mean, are we talking about a shallow, muddy layer of slush trapped between rock and ice? Or are we looking at a massive, abyssal, global ocean, tens or even hundreds of miles deep? Because an ocean that deep would completely dwarf even the deepest trenches we have right here on Earth. And think about this. What's actually protecting this water? How thick is the ice above it? Is it a thin, cracking shell that lets radiation and surface materials slip through super easily? Or is it a massive, impenetrable armor of solid ice that's miles and miles thick? Just thinking about the sheer scale of what we still don't know about these alien oceans is honestly pretty awe-inspiring. But out of all these variables, here is perhaps one of the absolute most critical structural questions of the whole bunch. Does the ocean touch the rocky sea floor? I really want to emphasize this because this isn't just some basic geography question. This is fundamentally about geological interactions. If the liquid water actually makes physical contact with the rocky core, you suddenly have the potential for rich chemical reactions, mineral dissolution, and heat transfer. Basically, you have the foundations for something incredible.
Which leads us seamlessly from the physical structure of the ocean straight into the dynamic movements happening inside it. Scientists are out here desperately trying to map out dynamic chemical exchanges. They're asking, is there chemical exchange between the ocean and the surface? Is there material traveling upward from the depths, maybe from hydrothermal vents? Is material from the icy, radiated surface traveling downward? And are there specific regions where energy is heavily concentrated? We're no longer just looking for a stagnant pool of water. We're trying to map a complex, churning, dynamic chemical engine, all without ever physically touching it.
All of those rapid-fire questions we just went through, the salt, the extreme depth, the protective ice, the rocky seafloor contact, the complex chemical exchanges, they all lead us, inevitably, to this single overarching question. Could any of these environments support life? Every single structural detail and dynamic movement we just listed is a necessary variable in the ultimate cosmic equation of habitability.
So the crucial point is, this isn't just theoretical musing on a whiteboard somewhere. These exact questions are the concrete driving forces behind actual space exploration today. NASA's specific mission objectives now explicitly mandate two main things. Number one, determine the properties of the ocean. And number two, understand how it interacts with the surface. They are actively dedicating time, huge resources, and brilliant minds specifically to solve the mysteries we've just been breaking down. Why? Because they know the old question just isn't enough anymore.
And those NASA objectives are incredibly specific for one massive reason. An ocean alone doesn't make a world habitable. We have this powerful bias, right? Earth has water, and Earth has abundant life, so we naturally tend to equate the two. But H2O is just the baseline. It's the blank canvas. The essential takeaway from Chapter 12 is that water, on its very own, simply isn't enough.
So let's look at how this builds. What are the true requirements for a habitable world? Think of it like a cosmic recipe. You don't just need liquid water. Step one, you need chemistry. You need the exact right chemical building blocks and reactions, which, by the way, is exactly why that rocky seafloor contact is so vital. Step two, you need usable energy, a power source to drive those chemical reactions, which is why we look for all that dynamic movement. And step three, you need stability. You need an environment that stays consistent enough, for long enough, for something as fragile and incredibly complex as biology to actually take hold.
If a distant, alien ocean has the water, and the chemistry, and the usable energy, and the stability, well then you finally have the complete recipe. And that leaves us with one final staggering thought. If we find a world in our solar system that actually checks all of these boxes, are we on the verge of discovering a second genesis of life, right in our own cosmic backyard? Let's bypass the hype and the sci-fi for a second and look at the raw, unfiltered science of Jupiter's moon, Europa.
In this explainer, we're diving into the temporal window of Europan life, 4 billion years of possibility. We're talking deep time, chemical potential, and honestly, the ultimate unsolved mystery of biology.
Okay, let's just sit with this number for a second. 4 billion. 4 billion. It's kind of hard to even wrap your head around, right? But that is the amount of time NASA scientists think Europa's subsurface ocean might have actually persisted. I mean, think about what that means. For practically the entire history of our solar system, this dark, liquid water ocean has just been sitting there, churning away beneath an icy crust. We're not talking about some temporary puddle. This is a vast, incredibly stable environment that's been hanging around for an almost unfathomable amount of time. And here's why that matters. If an ocean exists for a huge chunk of a world's history, the chemistry happening inside it has just an enormous amount of time to develop. It's not just about a moon simply having water. It's about having water for so long that molecules can bump into each other, break apart, recombine, and try out literally endless combinations. Time is the crucible of chemistry, you know? 4 billion years? That gives anything that could happen chemically the absolute perfect opportunity to actually do so.
So, moving into Section 1, 4 billion years, the power of deep time.
And that brings us to Section 2, the origin of life, a cosmic reality check.
Now, right here is where we really need to pause and confront a pretty humbling scientific truth. It is so easy to get totally swept away by the romance of an ancient ocean. You look at a 4 billion-year-old liquid environment, and obviously your imagination runs wild thinking about what kind of crazy stuff might be swimming around down there. But actually, we need to slow down. Time doesn't automatically create life. Let that really sink in for a second, because it's basically the anchor for everything we understand about astrobiology. Despite how hyped we get about a 4 billion-year-old ocean, we literally cannot just assume that vast amounts of time guarantee biology. Chemistry is chemistry, and biology is biology. You could leave raw chemicals in a giant ocean for 4 billion years, and it absolutely does not guarantee that something living is going to inevitably pop out of it. Time is a requirement for sure, but time alone isn't some magic wand that just forces life to happen.
Which brings us to our baseline reality, illustrated perfectly by the number 1. When we're talking about the origin of life, our sample size across the entire known universe is exactly 1, Earth. Our home planet is literally the absolute only world where we know for a fact that life exists. Every single thing we know about biology, about evolution, about what life needs to survive and thrive, it's all based entirely on what happened right here. So when we look out at Europa, we're kind of forced to look through an Earth-centric lens, simply because it is the only lens we actually have.
And because our sample size is just 1, we have this massive, gaping blind spot when it comes to figuring out how hard it actually is to spark life from raw chemistry. Like the slide says, we really don't know how easy or difficult the origin of life actually is. Maybe turning raw materials into life is something that happens all the time across the cosmos if the conditions are right, like a total cosmic inevitability. Or maybe it's a total freak accident, something so wildly improbable that it literally only happened once, right here on Earth. Since we honestly don't know how difficult that jump from non-living chemistry to living biology is, trying to predict whether there's life on Europa requires some pretty serious scientific humility.
Now, what's really fascinating is looking at these 3 main possibilities, because they perfectly highlight just how much we still don't know. Let's walk through them together. First, maybe life just begins whenever water, chemistry, and energy coexist for long enough. If that's the case, Europa is incredibly promising, right? It's got the water, the chemical building blocks, and obviously the time. But consider the second possibility. Maybe life requires a super rare sequence of events, a very specific chain reaction acting at exactly the right moment. If that's true, Europa might just be a sterile ocean full of interesting but completely dead chemistry. And then there's the third option, which honestly might be the most tantalizing of all. Maybe Europa has absolutely everything except one critical ingredient, just one single missing puzzle piece that keeps the whole biological engine from turning over. These 3 ideas, this is the absolute bleeding edge of what we're trying to figure out.
All right, let's head into Section 3, the beauty of uncertainty, embracing the unknown.
Now, I know it might feel a little frustrating to talk about this epic 4 billion-year-old ocean, only to admit how little we actually know about what's going on down there. But honestly, embracing that unknown is exactly what makes this science so thrilling. We simply don't know. And saying we don't know is arguably the most honest and exciting decision a scientist can possibly take when looking at Europa. It means the story isn't finished yet. It means the universe is still holding on to some massive fundamental secrets about our place in it. Think about it. If we already had all the answers, there'd be literally no reason to explore, no reason to launch these spacecraft, and definitely no reason to ask these huge, beautiful questions.
And that's why the actual unvarnished mystery of our solar system is infinitely more fascinating than any sensationalized science fiction story. On the one hand, you've got the fake alien stories, the hype, the imaginary creatures, and sure, those are fun, but they're entirely limited by human imagination. On the other hand, you have genuine scientific uncertainty. You have the real universe, with this completely silent, pitch-black, 4-billion-year-old ocean operating on rules we haven't even figured out yet. The actual reality of Europa, with all of its lingering mysteries, is just so much more gripping than anything we could possibly make up.
So, as we wrap up this explainer, I want to leave you with a pretty provocative question to chew on. If Europa has everything, what is the one critical ingredient it might be missing? As we keep studying this ancient ocean, we have to constantly ask ourselves what that final, elusive spark of life actually requires to ignite. Is it just waiting down there in the dark? Or is Europa just a beautiful, timeless, empty sea? Keep wondering, keep asking questions, and thanks so much for joining me to explore this incredible mystery.
Okay, let's dive right into this explainer. Today, we're exploring one of the absolute most tantalizing mysteries in our entire solar system. I'm talking about Europa. Beneath the thick, icy crust of this moon of Jupiter lies a vast liquid ocean. It's the kind of place that has completely captured the imagination of astronomers, biologists, and honestly, anyone who just looks up at the night sky and wonders, are we alone out here? But listen, we aren't here to speculate wildly today. We're here to look closely at the hard biological possibilities of Europa's hidden ocean.
So, what could actually be down there? Seriously, I want you to actively imagine the possibilities with me for a second. You've got this massive ocean, trapped in perpetual darkness, being constantly heated by the immense tidal forces of Jupiter. It's a totally alien environment, yet it holds the fundamental ingredients for life as we know it. So what is swimming, or floating, or maybe just existing in that dark abyss?
Well, before we let our imaginations run completely off the rails, we have to remember this core rule, not as facts, as scientific scenarios. This quote right here perfectly hits the nail on the head. It illustrates exactly how we need to approach this. We're looking at this through the lens of rigorous scientific hypotheses, not science fiction. Since we obviously don't have the final proof yet, we have to map out the potential realities. So let's break down the 4 main scientific scenarios of what might actually be happening on Europa right now.
Let's move to our first possibility. Scenario 1. Europa is completely sterile.
Okay, for a lot of people, this is probably the most frustrating possibility to even think about. But scientifically, it's absolutely crucial we start here. Europa has a seemingly perfect recipe. As you can see, the ocean exists. We know that for sure. The necessary chemistry exists, the energy exists, but life never began. It's a massive cosmic paradox, right? It tells us that just having all the right ingredients sitting there in the bowl doesn't guarantee the biological cake is actually going to bake. It is entirely possible that Europa has just been sitting there for billions of years, trapped beneath an ice shell up to 15 miles thick, acting as a massive, sterile chemical soup with absolutely zero biological activity.
Moving on to scenario 2, simple microbial life.
But what if that biological spark did happen? Now, when we hear the word life, human nature kicks in, and we immediately think of Earth. We picture lush forests, animals, or maybe even some secret underwater alien civilization. But Europa's reality? It's likely vastly different. If life managed to take hold down there, it's almost certainly simple microbial life. No giant sea monsters, just microscopic ecosystems surviving solely on chemical energy in total, absolute darkness. It's a pretty stark, humbling reality compared to the movies, but make no mistake, finding even that would literally be one of the greatest scientific discoveries in human history.
Now for scenario 3, extremely sparse life.
Imagine life did begin, but the conditions are just so incredibly harsh that it barely clings to survival. In this scenario, we wouldn't be looking at an ocean that's just teeming with life from top to bottom. Not at all. Instead, life remains completely confined to small pockets and highly localized environments. Think about the very bottom of Europa's ocean, right where that liquid water directly interacts with the rocky mantle underneath. That water-rock interaction, it could create these tiny, isolated oases of chemical warmth and nutrients. Life would be extremely sparse, scattered across a pitch-black seafloor, basically just scraping by in these tiny localized havens.
And that brings us to scenario 4, unfamiliar chemistry.
Now, what's really interesting about this scenario is that we step into the most mind-bending possibility of the whole bunch: radically different chemistry. This forces us to just completely throw out our Earth-centric rulebook. We're talking about a form of life on Europa that is entirely unfamiliar compared to anything we've ever encountered. And just to be super clear here, this doesn't mean we're talking about an advanced, intelligent civilization or even that it's highly complex. It just means its fundamental biological makeup completely defies our earthly understanding. It might not use the biological structures we expect at all. It's a huge reminder that the universe doesn't have to follow the rules of biology exactly as we know them here on Earth.
Which brings us to the ultimate scientific baseline.
So the crucial point is this: we need to pull back from our imaginations for a second and really ground ourselves. The ultimate scientific baseline is that Europa may have absolutely no biological life at all. Scientists have to actively avoid assuming life exists just because we desperately want it to. I mean, it's totally human nature to look at a dark, mysterious ocean and automatically fill it with life in our minds, right? But the baseline for any true investigation of the unknown has to be a blank slate. We have to be perfectly prepared to send our probes, break through all that ice, and find absolutely nothing biological whatsoever.
Which leads perfectly into our final thought for this explainer. Scientists cannot decide the answer before the evidence arrives. That right there is the absolute core of the scientific process. We've mapped out the scenarios today, from a completely sterile ocean, to simple microbes, to sparse pockets of survival, to radically unfamiliar chemistry. But until we actually get down there and analyze what's beneath the ice, every single one of these remains exactly that, just a scenario. Which really begs the ultimate question: if we do break through that ice one day and find life staring back at us in the dark, what does that mean for the billions of other icy worlds scattered across the cosmos? Okay, let's dive into this. Welcome back to The Explainer. Today we're jumping right into the text, Surveying the Unseen Ocean. Specifically, we're zooming in on Chapter 22 and the massive buzz surrounding the upcoming Europa Clipper mission to Jupiter's icy moon. Now, if you've been following the news, you probably have this sci-fi movie image in your head of how we're going to pull off exploring an alien ocean. It's an incredibly cool thought, but as the source material points out, the reality completely flips that expectation on its head. And honestly, it's actually way more fascinating. So let's unpack what this spacecraft really is, and just as importantly, what it definitely isn't.
So the big question: are we sending a submarine to Europa? It is hands down the most common thing people ask when they hear there's a giant liquid water ocean hiding under Europa's ice. And I mean, it makes total intuitive sense, right? Down here on Earth, if we want to explore the deep, unexplored ocean trenches, we send a submersible. We build a super strong hull, slap on some propellers, and down we go. But Chapter 22 goes out of its way to completely shatter that idea. We are absolutely not doing that. To really get what the Europa Clipper mission is about, we kind of have to toss our earthbound instincts right out the window.
In fact, the text actually titles this specific section, "We are not going down there." It opens with this bold, almost in-your-face declaration that there is one final major misconception about this mission that we need to completely destroy right now. They call it the grand misconception. Look, as a society, we absolutely love the idea of a Jules Verne-style sci-fi adventure. You know, the whole plunging into the dark, mysterious depths of an alien moon. It's romantic. But the brutal reality of space exploration, especially when you're dealing with those intense, harsh conditions all the way out at Jupiter, demands a totally different approach. To really appreciate the sheer genius of the Europa Clipper, we've got to permanently strip away this whole myth of the deep-sea dive.
The text gets incredibly explicit here. The Europa Clipper is not a submarine. It will not drill through the ice. It will not physically enter the ocean. And it will not swim through Europa's water, period. None of that is happening. No massive thermal drills melting through miles of crust, no robotic fins, no swimming in the alien dark. It is absolutely crucial that we wipe that whole submarine image from our minds right now. To understand the actual physical mechanics of this unprecedented mission, we have to completely rethink our relationship with the water we're trying to study.
Now, what's really interesting about this slide is the stark contrast it sets up. We are completely trading in all those physical, tactile actions we just debunked, the drilling, the swimming, the entering, that's the submarine myth. Instead, we're looking at the remote observer reality. The source outlines this truly astonishing pivot. Instead of swimming, humanity is going to study a massive alien body of water without ever actually touching it. Not a single drop. We are entirely replacing that physical deep-sea dive with the highly calculated observation of an orbiting spacecraft. We're going to learn the secrets of the deep, literally from high above the ice.
So naturally, that brings up a seemingly impossible riddle.
How on earth do you measure a massive body of water that you cannot touch, and that's buried under miles of solid, frozen ice? If we aren't using a submarine, what is the alternative here? Well, the answer is basically a masterclass in remote sensing. It's a sensory arsenal unlike anything we've ever deployed. Instead of a heavy, pressure-proof hull, the Europa Clipper is packed with an array of incredibly sensitive scientific instruments. These tools are meticulously designed to act as our digital eyes, ears, and hands across the freezing void of space.
And here is exactly how we map the unseen. The Clipper is going to pull this off by measuring a whole symphony of invisible forces. First, it's measuring gravity and magnetic fields, which actually shift and react to that massive conductive saltwater ocean hiding below. It'll use radar reflections to literally ping signals through the ice and listen for the echoes of liquid water. It's catching infrared and ultraviolet light to read the surface composition. It's analyzing trace matter, scooping up ambient dust, sampling escaping gases, mapping the surface chemistry to see if the ocean is leaking through. It's hunting for thermal signatures, looking for warm spots in the frozen shell. And perhaps it will even capture actual plume material erupting right out into space. Just think about that stack of techniques for a second. By combining all of these remote measurements, feeling invisible forces, reading light, catching matter, scientists can piece together a highly detailed picture of an ocean from millions of miles away.
And this brilliantly illustrates a powerful quote directly from the text. This is one of the strangest forms of exploration humanity has ever attempted. Just let the philosophical weight of that sink in for a moment. Historically, humanity explores by going to a physical place. We stand on a new continent, we float in a sea, we walk on the moon. But here, we are fundamentally redefining what exploration even means. We are sending our robotic senses out into the dark, cold vacuum of space, and we're reconstructing a dynamic, alien marine environment entirely through data, invisible forces, and light.
It all leads up to this profound, almost poetic realization about what we are actually capable of. Through decades of engineering, cutting-edge technology, and just brilliant problem-solving across the globe, we are about to do something that honestly borders on magic. We will investigate an ocean without ever seeing the ocean. It is the ultimate paradox of this mission, and the brilliant core of Chapter 22. We're going to map its unseen currents, we'll know its depth, we'll understand its chemistry and its potential to harbor alien life. And we'll do all of this while the water itself remains completely hidden, locked away beneath that thick, impenetrable shell of ice. We are literally feeling our way through the dark. But we're doing it using math, physics, and pure human ingenuity to illuminate a world that has been hidden in shadows for billions of years.
Which leaves us with a truly mind-bending final thought to wrap up today's explainer. If we can uncover the deepest secrets of a massive alien ocean that we cannot even see, using nothing but gravity, light, escaping gases, and magnetic fields, what else in the universe is waiting to be felt rather than touched? What other invisible worlds and ancient cosmic mysteries are we going to discover when we finally learn to look with these entirely new senses? It totally changes how we view our place in the cosmos. Keep that thought with you, and thanks for joining me to explore this incredible material.
All right, let's dive right into this. Welcome to our latest explainer. Today, we're focusing on one of the absolutely most mysterious and captivating places in our entire solar system, Jupiter's ice-covered moon, Europa. We are standing squarely on the verge of new discoveries that are going to completely dictate the story of this world. Basically, decades of wild speculation are finally about to meet cold, hard data. And according to Chapter 19 of the recent planetary literature we're unpacking today, the path forward isn't just some infinite web of guesses. It's actually highly structured. So we're going to look closely at the exact outcomes scientists are preparing for right now and exactly how they plan to interpret the data we get back.
But hey, before we get into the nitty-gritty of the hard science, let's just pause for a second and consider the sheer monumental stakes here. What happens if we actually find life on Europa? I mean, it's a question that completely shifts our entire understanding of our place in the universe. Think about it. If life can independently arise twice in one single solar system, once on a rocky world close to the sun, and then again in a dark, icy ocean millions of miles away, then the universe is likely just teeming with it. It's a pretty heavy thought, right? But to get to that answer, we can't just rely on hope. We have to rely on rigorous, uncompromising science.
So the crucial point here is that we need a framework to understand whatever data we end up receiving. According to our focus material, scientists have actually narrowed down the future of Europa's exploration to exactly 3 fundamental discoveries, 3 distinct paths that could fundamentally change the entire story of Europa. Every single thing we find is going to fall into one of these 3 buckets, and understanding these 3 potential revelations is literally the key to understanding the entire mission.
So let's start with Revelation 1, less habitable.
Okay, I know, this might not be the blockbuster sci-fi headline we're all secretly rooting for, but we have to ground ourselves in reality here. This is a very real, somewhat disappointing, but entirely scientifically valid possibility that Europa's ocean is just much less hospitable to life than we initially expected. If this first revelation comes to pass, it means a few very specific things are happening beneath that ice. First, the chemistry just isn't right. The essential building blocks for life, at least as we understand it, just aren't there in the right proportions. Second, the energy isn't sufficient. Life requires a metabolic engine, and without enough energy, that engine simply cannot run. And third, the ocean may be entirely isolated. Think about what that implies for a second. An ocean totally cut off, completely lacking the crucial interactions you'd need to spark biology. If this is the case, it would severely narrow our possibilities moving forward. We'd basically be looking at a quiet, static, frozen world.
Now, let's look at Revelation 2, much more active. Instead of a silent, isolated ocean, imagine a highly dynamic, energetic, and just chaotic world beneath that icy crust. We would see way more exchange between the surface and the ocean, like a living, breathing connection between the ice up above and the deep down below. We would witness more water movement, perhaps massive currents just churning in the dark. There would be more chemical cycling, creating this rich, complex soup of interacting elements. And driving all of this whole shebang, more internal energy. This revelation would make the moon even more incredibly interesting to study. It really sets the stage for a world that is practically begging to be explored further.
And then we have Revelation 3, the paradigm shift.
This is the door we are all holding our breath to open, the outcome that completely redefines human knowledge. Evidence consistent with biological activity. Just let that sink in for a moment. This is the single monumental discovery that would truly change everything. Not just a more active ocean, not just some interesting chemistry, but actual evidence of biology. It is the literal climax of centuries of astronomical dreaming. But here is exactly where we need to pump the brakes and do a really sharp reality check. Is seeing truly believing? Because in the realm of astrobiology, extraordinary claims require an incredibly rigorous burden of proof. We can't just spot something weird on a sensor and immediately declare we found aliens, right? The scientific method demands a massive gauntlet of verification. So let's look at exactly what scientists say would absolutely not be enough to prove this third revelation.
Our source is incredibly clear on the inadequacy of isolated clues. Let's say we find a highly unusual chemical signature. Well, one strange molecule wouldn't be enough. It's a tantalizing hint, for sure, but it's not proof.
Let's say we spot water literally shooting out of the ice into the vacuum of space. As spectacular as that sounds, one potential plume wouldn't be enough. Normal, everyday geology can cause plumes without any biology being involved at all. And what if we find the very stuff of life itself? Still, one organic compound wouldn't be enough. Actually, non-living chemical reactions can create organics all the time out in the cosmos. Finding a single one of these things falls entirely short of proving that life actually exists. Which brings us to the burden of proof, extraordinary evidence. To actually claim we have found life on Europa, scientists would need extraordinary evidence. You simply cannot rely on a single anomaly. The strongest, most irrefutable discovery demands multiple, independent lines of evidence that are all pointing to the exact same conclusion. First, the chemistry has to be undeniable. We're talking a complex web of biological signatures, not just one weird molecule. Second, the context must be right. The environmental surroundings around it must logically support a living ecosystem. And third, patterns. We need to see repeating biological patterns that show a sustained, organized process, not just a random chemical fluke. All three of these pillars must be present. Which brings us to the ultimate scientific hurdle. We need evidence that cannot be reasonably explained by non-biological processes. That is the golden rule here, folks. Before we can declare we have found life on Europa, we must completely, systematically rule out every single non-living explanation. Geology, exotic chemistry, radiation, all of it must be eliminated as the clause. Only when biology is the absolute only reasonable explanation left standing can we make the claim that changes everything. Which leaves us with this final thought for today's explainer. If we actually cross that impossible hurdle, if we somehow find evidence that non-biological processes truly cannot explain, are we ready for what comes next? It's a profoundly heavy implication just waiting for us in the dark waters of Europa.
We've got the framework, we know the 3 possible revelations, and we know the impossible burden of proof required. Now, we just have to go look. Thanks so much for joining me on this deep dive, and keep your eyes on the ice. Welcome to This Explainer. Okay, I want you to take a deep breath and just settle in for a second, because today we are diving into one of the most profound, unsettling, and honestly strangely beautiful cosmic mysteries you can imagine. You know, when we look up at the night sky, we're basically conditioned to imagine a universe just brimming with potential. We see the stars, the planets, the moons, and we naturally assume that, hey, biology is just an inevitable consequence of the right cosmic conditions. But today, we're looking at some fascinating source material from The Silence of the Moons, specifically Chapter 21, which is so perfectly titled The Opposite Possibility. We're going to take our standard cosmic perspective and flip it completely upside down. It's one of those questions that just stops you right in your tracks, isn't it? What if Earth is extraordinarily rare? I mean, we spend so much time searching the cosmos, sending out radio signals into the dark, scanning the atmospheres of all these distant exoplanets, and we do all of this operating under this massive assumption that if the stage is set, well, life is inevitably going to make an entrance. We assume the universe is this crowded theater. But this text challenges us to really confront the silence. What if the bustling, vibrant biology we see outside our windows right now is not the cosmic rule, but actually the ultimate staggering exception? Okay, let's dive into this. Section 1. The opposite possibility. When assumptions fail. Moving right along to Section 2. A beautiful, lifeless ocean. Europa's hidden depths. So let's talk about Europa. It's one of Jupiter's moons, and it has long been the absolute crown jewel in our search for life. In astrobiology, we have this fundamental assumption, kind of a golden rule, really, where we just follow the water. Beneath Europa's icy crust, there is a massive liquid water ocean. And in our minds, we've already populated that dark sea with all sorts of crazy, speculative biology. Now, what's really interesting about this is, well, look at these characteristics straight from the source text. It suggests that perhaps Europa's ocean is beautiful, it is ancient, it's highly chemically active. The ingredients are all right there, swirling and interacting in the dark for absolute eons. And yet, the text presents the stark possibility that it is completely lifeless. Just sit with that incredible contrast for a second. A world of dynamic, majestic chemistry, a vast ocean just churning away, utterly devoid of even a single solitary microbe. The text states it so perfectly right here. Perhaps liquid water can survive for billions of years without producing biology. If that turns out to be true, the author notes that would also be profound. And it really would be, right? Because for decades, we've treated liquid water as a sort of magic elixir. The assumption has always been that if you just leave water alone for long enough, biology is just the natural byproduct. But this opposite possibility suggests that water can just be water for billions of years, just a completely sterile, silent sea.
Which brings us to Section 3, the missing ingredient, the limits of our recipe for life. The text really breaks down the staggering implications of a dead Europa. Step 1. Water isn't enough. The great solvent, the absolute cradle of Earth's biology, is completely insufficient on its own. Step 2. Energy isn't enough. Think about all that chemical activity, the intense churn of that hidden ocean, the potential hydrothermal vents, all of that immense power yielding absolutely nothing. And perhaps most sobering of all, Step 3. Time isn't enough. Even given billions of years to just endlessly roll the cosmic dice, biology isn't a guaranteed outcome. The universe can literally wait forever, and life still might not spark.
So the crucial point is exactly this. Something else is required. Something we just don't yet understand. This right here is the heart of the mystery that the source text is revealing. There has to be a hidden trigger, some kind of spark for biological genesis that goes way beyond just having water, energy, and time. But what is that spark? Is it some highly specific, free chemical reaction? Maybe a sequence of events so vanishingly improbable that it literally only ever happened right here on Earth? The text doesn't give us the answer, mostly because humanity simply doesn't have it yet. It just leaves us staring straight into the profound unknown of that missing ingredient. And that leads right into Section 4, a moon-sized laboratory, the ultimate natural experiment. The text frames this perfectly. A laboratory the size of a moon. We're so used to conducting our science experiments in these tiny little beakers and petri dishes, inside sterile, temperature-controlled rooms down here on Earth. And this brilliantly illustrates how, as the text describes, Europa itself becomes a natural experiment.
It's an entire world serving as a baseline control group for the rest of the universe. It is a massive, planetary-scale test tube where the fundamental mechanics of chemistry have been allowed to just play out entirely on their own. And this experiment has been running for billions of years. I mean, just really try to wrap your head around the sheer scale of that time. A world that has been running for billions of years without humans watching? Zero contamination, absolutely no interference. Just the raw, silent mechanics of the cosmos grinding away in the pitch black of those ocean depths. It's this unbroken, pristine chain of chemical history, sealed tight beneath a giant vault of ice, quietly existing while entire species on our own planet rose and fell. Until now. Those two words from the text just carry so much weight. For billions of years, this moon-sized laboratory has operated in total isolation, completely unobserved. But we have finally arrived at a point in human history where we can actually look inside. And whether we find a bustling alien ecosystem down there, or the profound, silent majesty of a completely lifeless, chemically active ocean, well, our understanding of our own existence is about to change forever. So I'll leave you with this one final thought to ponder. If we peer into Europa's dark waters and find absolutely nothing looking back, what does that profound silence finally tell us about the miraculous, highly improbable, and extraordinarily rare gift of life right here on Earth? Hey everyone, and welcome to The Explainer. Today, we're zeroing in on one of the absolutely most thrilling, but honestly most frequently misunderstood topics in modern space exploration. We're talking about the search for life beyond Earth, specifically looking at places like Jupiter's icy moon Europa. Just saying the name Europa kind of sparks the imagination, doesn't it? It represents the unknown, the edge of our cosmic neighborhood, and that tantalizing possibility that we might not be alone in the universe. But as we explore the stars and get all this new data, there's a massive trap that both the media and the public fall into time and time again. It's a conceptual trap that totally skews our understanding of what scientists are actually doing out there. Okay, let's dive into this. A dangerous misunderstanding. Whenever a new space discovery drops, there's this one specific phrase buried in the media hype that is just incredibly exciting to hear. Scientists will proudly announce, Europa has the ingredients for life. I mean, wow, just listen to that phrase. It literally sends a chill right down your spine. It sounds like the prelude to the greatest discovery in human history. When you hear ingredients for life, your brain immediately starts painting these vivid pictures of alien ecosystems swimming around beneath the ice. It's a phrase practically designed to highlight the profound potential of a world.
And this brilliantly illustrates the core issue we're dealing with. On one hand, we have what scientists literally say, based strictly on their hard data, Europa has the ingredients for life. But on the other hand, we have what the general public actually hears when they read that. People hear, Europa has life. I've got to be absolutely clear here, folks. Those are not the same statement. They aren't even close. Mistaking one for the other is the fundamental misunderstanding we have to correct today.
So what can science actually detect?
When we fling these incredibly complex probes millions of miles out into the dark, what are they physically measuring? Let's run through this amazing checklist of things scientists can actually detect right now. First up, water. We're talking massive, deep subglacial oceans. Second, carbon-containing molecules, the literal organic building blocks of biology. Third, energy sources, like hot hydrothermal vents churning deep beneath the ice. And fourth, chemical gradients, the actual differences in chemistry that could act like a battery to spark and sustain biological processes. Ticking off these boxes is just a staggering triumph of human engineering and science.
But, okay, I have to pull the enthusiasm back for a second, because here is the hard truth. You can check off every single one of those amazing, exciting boxes. You can find the water, the carbon, the energy, and the gradients, and you can still have absolutely zero evidence of biology. None. It's like just having flour, sugar, and eggs sitting on your kitchen counter doesn't magically mean you have a baked cake, you know? The ingredients are just the prerequisites. They are not the biology itself. Let's move to and see how this builds. Habitable versus inhabited. You see, the absolute hardest step in astrobiology is crossing the huge gap between these two very different concepts. On one side, we have habitable. That simply means a location is capable of supporting life. The conditions are right, the ingredients are sitting there on the counter. But on the flip side, we have inhabited. That means life is actually present, biology is actively happening. Going from habitable to inhabited is the hardest part of the equation.
That gap is enormous, and crossing it is an incredibly difficult scientific threshold to prove.
To ground this whole theory in reality, let's look at the Europa Clipper mission. We are literally about to send this incredibly sophisticated spacecraft out to Jupiter's orbit to perform dozens of close flybys of Europa. But we have to be super precise about what it's built to do. The Europa Clipper is primarily designed to characterize habitability. Its primary goal is strictly to look at the habitable side of that massive gap we just talked about. It's going to confirm the ice thickness, investigate the subsurface ocean, and analyze the chemistry of the moon. It is meticulously checking for those ingredients. It is not designed to look at the inhabited side. Now, what's really interesting about this slide is how totally unambiguous NASA is about this fact. They state it clearly right out in the open. The spacecraft does not carry a dedicated life detection instrument. NASA is telling us up front exactly what their tools can and cannot do. They are actively trying to manage our expectations and prevent the exact misunderstanding we've been talking about. So why does all of this matter to you? It comes down to reading future headlines.
Because as a consumer of science news, this knowledge basically acts as a filter. Fast forward a little bit, the Europa Clipper reaches its destination, it begins running its scans, and the data starts beaming back to Earth. You are inevitably going to see a breaking news headline that looks exactly like this. Europa Clipper found organic molecules. It'll be all over your feed. The excitement will be completely palpable, and yeah, it'll be a monumental day for science.
So the crucial point is how you react to that headline. When you see Europa Clipper found organic molecules, on one side, you will now know for a fact that it absolutely does not mean the headline on the other side, aliens discovered. Finding organic molecules is an incredible confirmation of habitability, sure, but it does not bridge that enormous gap to being inhabited. The presence of carbon-containing molecules simply does not equal the discovery of alien life. The big takeaway here is that science has to be much, much more careful. True science is methodical, it's rigorous, and it refuses to just jump to wild conclusions, no matter how badly we all want to find life out there in the dark. We really have to separate the media sensationalism, which, let's be real, thrives on clicks and dramatic leaps in logic, from the actual incredible facts that science is carefully uncovering step by step.
Which leaves us with this final, vital question. When the next big space headline drops on your feed, will you know the difference between a habitable world and an inhabited one? I really hope this explainer has empowered you with the exact knowledge you need to navigate these incredible discoveries. The universe is fascinating enough without us having to exaggerate it. Keep seeking the truth, keep looking up, and thank you so much for learning with me today.
Welcome to the Explainer. Okay, let's just dive right into this, because today, man, we are embarking on a truly incredible journey. We're looking at one of the most anticipated space missions of our entire generation, heading straight for the frozen, cracked shell of Jupiter's moon, Europa. We're going to explore the profound silence of Europa's ocean.
But before we launch, I want to start by asking you to think about something that's maybe a little uncomfortable. What happens if our greatest mission to find life finds absolutely nothing? It's kind of a heavy thought, right? We pour literal years of human genius and just massive resources into this singular goal of finding aliens, and we come up completely empty-handed. Does that mean we failed? Just keep that in the back of your mind as we go.
Section 1. The Clipper arrives.
So, imagine the Europa Clipper spacecraft finally reaching its destination after this immense, silent journey through the vacuum of space. The expectations here are just astronomical. The entire scientific community is literally on the edge of their seats, waiting for those very first packets of data to beam back to Earth. And once it arrives, the Clipper wastes no time at all. It gets right to work. It maps the ice, it measures the magnetic field, it examines the surface, it studies the chemistry. The probe is operating at this breakneck pace, meticulously scanning and measuring every single inch of this frozen world. The stakes are high and the work is totally relentless.
Section 2. The Big Plot Twist. Okay, let's fast forward a bit. Years have passed since the Clipper first arrived. The probe has diligently gathered all of this incredible data, and back on Earth, scientists have patiently crunched the numbers. And the result of all that waiting? There is no convincing evidence of life, just a deep, profound silence from Europa's dark ocean. I really want you to let that perceived disappointment sink in for a second. For a mission totally built around the tantalizing possibility of astrobiology, finding a completely lifeless ocean initially feels like, well, a crushing defeat.
Which brings us to a really critical question, one that kind of forces us to confront our own natural biases about space exploration.
Would the mission fail? If a mission like this doesn't find the life it was hoping for, is the whole thing suddenly a failure?
The answer to that is a resounding, definitive no. Absolutely not. In fact, finding nothing could still mean it was one of the most important planetary science missions ever flown. Let's pivot and look at exactly why a totally lifeless Europa is still an absolute monumental triumph.
Section 3. How ocean worlds work.
It all comes down to what we're actually discovering beneath the ice. We need to completely reframe our definition of success here. We're shifting away from the simple binary question of, hey, are there aliens? And looking instead at the incredible core scientific value of the data we're getting. Because even without life, we're uncovering the baseline mechanics of an ocean world. We are getting the physical, chemical, and thermal blueprints of a hidden subterranean sea. We're talking about learning the ins and outs of energy flow and entirely sunless chemistry.
So the really crucial takeaway here is that scientists would learn the fundamental rules of these extreme environments. They would learn how water survives under miles of solid, freezing ice, how energy moves through a seemingly dead, icy moon, how chemistry evolves entirely without sunlight. Ultimately, they'd learn how ocean worlds behave. And that constant stream of discovery, that builds into a revolutionary foundational knowledge base for all of planetary science.
Section 4. A universe of ice.
So why does that baseline knowledge matter so much? Well, because we need to zoom out. The grand scale of this discovery is that Europa isn't just some isolated anomaly. It's part of a much larger cosmic family. Just look around our own solar neighborhood. Other icy moons exist right here. We've got Enceladus, we have Ganymede, we have Callisto, and Titan, which has its very own wildly complex chemistry. If we understand the mechanics of a lifeless Europa, we suddenly possess a literal Rosetta Stone for decoding the behavior of all these other icy neighbors in our solar system.
But our perspective needs to stretch even further than that, because beyond our solar system, planets orbit other stars. There is a massive universe of exoplanets out there. And the detailed data we pull from a lifeless Europa stretches far, far beyond our own solar neighborhood, giving us vital clues to planetary systems deep in the cosmos.
Which leads us to this massive realization. If ocean worlds are common, then Europa may actually be teaching us about an entire category of worlds. By understanding the foundational rules of just one lifeless ocean world, Europa basically becomes the master blueprint for understanding an entire class of celestial bodies scattered all across the galaxy. It's the key to unlocking how a major portion of the universe actually operates.
So, I want to leave you with this final, kind of profound thought. How many of these hidden oceans exist in the dark of space, just waiting to be understood? Even if Europa's ocean turns out to be entirely silent and lifeless, it teaches us the fundamental language of these deep, dark waters. And once we know the language, we're finally ready to listen to whatever the rest of the universe has to say. Thanks for joining me for this explainer today, and never stop questioning what lies beneath the surface.
Okay, let's dive into this. Welcome to the Explainer. Today, we're embarking on humanity's next great voyage, and we're tackling what I like to call Chapter 23, The Final Question. We're heading out to Jupiter's moon, Europa. Now, as we look at this world, I really want you to picture the almost cinematic mystery of this place. We aren't just looking at some random rock floating in space. No, we are looking at the absolute frontier of human discovery. This is a place that holds the potential to answer literally one of the oldest questions we've ever asked ourselves as a species. But, to really grasp what we're doing here, we first have to understand the sheer, mind-boggling scale of what we're up against.
Hundreds of millions of kilometers away. Just let that staggeringly vast distance sink in for a second. We are plunging far, far beyond our comfortable little planetary neighborhood, way out into the deep, isolating darkness of the outer solar system. It is an incredibly lonely, silent journey just to reach Jupiter's orbit. We're talking about a world so remarkably remote that just pinging a message back and forth takes a significant amount of time. It's the very definition of isolation out there.
And when you finally cross that immense distance, what do you actually find? Well, looking at the brutal facts here, at first glance, Europa is an utterly hostile, desolate world. We're talking about a global ocean, yes, but it is completely entombed. It's hidden beneath kilometers of dense, unforgiving ice. And the surface above that ice? It's being constantly bombarded by Jupiter's intense radiation. It's a relentless, deadly environment that would absolutely destroy unshielded machinery, let alone delicate biology. And of course, the whole place is just unimaginably cold. So you might be wondering, why are we even talking about this frozen wasteland?
And yet, Let's just drop the pace here and pause on those two words for a moment. Despite the lethal radiation, despite that thick armor of ice, and despite the unimaginably cold environment, there is a massive contradiction at the heart of this entire world. Those two words, and yet, they open the door to what is arguably one of the most thrilling scientific possibilities of our time. Because beneath that terrifyingly harsh exterior, Europa is hiding a huge secret.
And this brilliantly illustrates why Europa is such a tantalizing target. According to the data, some of the very basic ingredients associated with life might actually exist right there on that harsh moon. It holds the ultimate recipe: water hidden down in that vast subsurface ocean. Chemistry, the fundamental building blocks required for complex reactions. Energy, a vital source of heat and power to drive those reactions. And time, billions of years of stability for all these elements to interact. It's a perfect, totally hopeful recipe, but having the ingredients laid out on the counter isn't exactly the same as having a fully baked cake, right?
Which brings us to the most relentless, driving force of science. We don't know. To truly understand Europa, we have to confront the massive limits of our own knowledge. We have the recipe, sure, but we're missing the crucial details. Over these next few beats, we're going to look at the staggering list of blind spots we currently have, starting with the very environment itself.
We don't know how deep the ocean actually is. Is it a shallow sea barely clinging to the rocky core, or is it a profound, bottomless abyss holding way more liquid water than all of Earth's oceans combined? The true depth of these hidden waters fundamentally changes how we understand this entire world. We don't know exactly how thick the ice shell is everywhere. Is it a thin, fragile crust in certain spots that might actually let us peek inside, or is it an impenetrable, miles-thick protective barrier wrapping the entire globe?
We don't know whether hydrothermal vents exist. This is a massive piece of the puzzle. Do those necessary heat sources, the engines for the energy and chemistry we talked about in our recipe earlier, actually sit down there on the dark ocean floor, churning out nutrients, just like they do deep in our own oceans?
We don't know how efficiently material moves between the surface and the ocean. Think about this crucial unknown for a second. Does the radiation-baked chemistry on that harsh exterior ever actually make its way down through the ice to feed the hidden interior? Is there some sort of conveyor belt of material, or are those two zones completely cut off from one another?
We don't know whether Europa's possible plumes are persistent. We've seen hints of water erupting out into space, but are these geysers a constant, reliable feature we can just fly a probe right through and taste? Or are they just a fleeting phenomenon that we might miss entirely?
And because of all those cascading mysteries, the depth, the ice, the vents, the plumes, we arrive at the ultimate question that drives this entire scientific endeavor. We don't know if life exists, period. That is the grand mystery. After all the ingredients and all the unknowns, we simply do not have the answer to the biggest question of all.
But let's move to and see how this builds. Because this is where the story shifts from passive mystery to triumphant action. The uncertainty isn't a dead end, it's an invitation. We are finally sending a machine capable of asking much better questions. We're no longer just guessing from afar. We're sending dedicated hardware, literally equipped with the most advanced instruments humanity has ever built, to pierce that veil of ice and give us hard data. And honestly, perhaps that is the most exciting part of this entire endeavor.
Now, what's really interesting about this slide is how it frames our expectations. It's so easy to get caught up in science fiction, but the true scientific value here is clear. Europa isn't promising us aliens. We need to be very, very clear about that. It isn't a guarantee of little green microbes waving up at a camera lens. Instead, it's promising us something vastly more valuable to the scientific process. It's promising us the rigorous pursuit of hard facts. It is promising us evidence.
So the crucial point is this: we don't know what the first detailed measurements will reveal. When that machine finally arrives, when those instruments first power on and taste the environment of Europa, what is the data going to say? Will it confirm our greatest hopes? Or will it present us with an entirely new set of mysteries we never even thought to ask? We're standing on the precipice of a completely new era of understanding, driven entirely by the search for evidence. So I'll leave you with this: what do you think those first detailed measurements will reveal?
Hey everyone, and welcome to This Explainer. Today we're looking at a world that is going to force us to completely rethink our place in the cosmos. There's a really deep, almost profound reason why Jupiter's moon, Europa, matters so much to scientists right now. It represents a fundamental shift, one that could, quite literally, change our entire idea of what life actually is.
Which brings us to a pretty massive question. Have we been looking for aliens in the completely wrong places? I mean, for most of human history, when people imagined extraterrestrial life, our brains naturally defaulted to a very specific set of assumptions, right? Assumptions built entirely around our own experience here on Earth. But what if the universe is just far more creative than we ever gave it credit for?
Okay, let's dive into this. Historically, when we imagined alien civilizations, we always pictured these rocky worlds, didn't we? We pictured creatures living out their lives under the warm glow of some alien sun. Classic sci-fi stuff. But Europa suggests a completely different possibility. It suggests that life might actually exist in worlds that look completely, entirely hostile from the outside. We're talking about life thriving under miles of ice, in absolute pitch-black darkness, and powered entirely by chemistry.
Just think about the sheer physical reality of this for a second. Europa is a world completely separated from the vacuum of space by kilometers of frozen material. If you were in a spaceship and flew right past it, you'd just see a cracked, dead-looking ball of ice. Nothing special. But hiding right beneath that incredibly thick frozen shield is a potentially habitable environment, completely veiled in darkness. It totally subverts our expectations of what a living world is supposed to look like.
So, the crucial point is that we really have to adjust our expectations here. We aren't looking for sprawling, futuristic cities hidden beneath the ice. The reality is probably much, much smaller, but honestly, it's just as profound. We're talking about microbial life. Finding even a single microscopic biological entity surviving in that isolated dark ocean would absolutely be the greatest scientific discovery in all of human history. No exaggeration.
And here is where we really need to zoom out and look at the entire cosmos. Because if microbial life exists down there in Europa's ocean, well then the universe might contain far more habitable environments than we ever previously imagined. Think about it. If life doesn't actually require a warm surface and a nearby star shining down on it, our entire statistical model for a habitable universe just drastically, massively expands.
And this brilliantly illustrates a really key point, because the fundamental ingredients are basically everywhere. Icy worlds, they're extremely common across the cosmos. Water may very well be common too. Organic chemistry, the carbon-based building blocks of life, that's common. And energy sources like gravitational friction stretching and squeezing the moon or geothermal heat, also common. The fundamental ingredients for a European-style environment are just incredibly abundant out there.
So here's how the logic flows, step by step. You start with vast amounts of frozen material, basically acting as a giant shield protecting an inner world from the harshness of space. Beneath that shield, you've got energy sources creating heat, which powers active organic chemistry in just absolute darkness. These ingredients are mixing, they're reacting, churning away without a single ray of sunlight. And then comes the ultimate theoretical leap. In that deep, dark chemical soup, chemistry somehow crosses the boundary into biology.
Which brings us to what is essentially the ultimate scientific precipice. If the ingredients are so common, and these hidden isolated oceans are common, how often does chemistry actually cross that boundary into biology? Is life just some bizarre cosmic fluke, like a 1 in a trillion lottery ticket? Or is it just a natural, almost inevitable consequence of chemistry doing its thing?
The truth is, we don't know. And we just have to sit with that for a second. That is the stark, awe-inspiring reality of where we currently stand right now. For all of our wild technological advancements, humanity has yet to actually discover the answer to that fundamental question.
But Europa may help us begin answering that. That cracked, frozen little moon sitting right in our own cosmic backyard holds secrets that could completely redefine what it means to be alive. If we can just pierce that ice and understand the chemistry happening down there in the dark, we might finally learn the truth. Because if we find something, anything, surviving in that alien ocean, we really have to ask ourselves, if life can take hold in the cold, crushing dark of Europa, where else is it hiding?
Hey everyone, and welcome to today's Explainer. Today we are diving into something literally out of this world. We're zeroing in on a truly monumental moment of scientific discovery, the unlocking of Europa's hidden ocean. We're going to break down exactly what that moment is going to look like, what it'll feel like, and most importantly, what it means for all of us right here on Earth. So let's set the stage for one of the absolute most anticipated events in modern space exploration.
So I want you to imagine something with me. The year is 2030.
I want you to really project yourself into that near future. This isn't some science fiction story set centuries from now. This is quite literally right around the corner. We are placing ourselves at the exact moment a journey of incredible distance and ambition finally reaches its destination.
Here is how this plays out. First up, our spacecraft, the Europa Clipper, finally reaches Jupiter. But, it doesn't just hang around there admiring the view, it kicks off its mission immediately, taking that crucial next step to physically approach Europa itself. It's a very methodical, sequential arrival that brings humanity right to the doorstep of this icy moon.
Now you got to keep in mind, this is absolutely not a peaceful, quiet flyby. As the spacecraft gets closer and closer to Europa, it is plunging straight into a highly volatile, violent environment totally dominated by Jupiter. The radiation out there is intense. It's brutal, and the spacecraft just has to endure this to do its job.
Section 1. Instruments awake in radiation.
Against all of these immense odds, the mechanical heart of this mission just wakes up. The instruments switch on. You've got cameras immediately collecting images. The magnetometer fires up to start measuring. Radar starts punching waves right down into the thick ice. Meanwhile, MassPax is out there sniffing and sampling the surrounding gases, and Suda starts examining the dust. It's this beautiful, highly coordinated awakening designed to capture every single metric possible all at once.
Section 2. The long wait on Earth. And while all that high-tech, mind-blowing action is happening way out by Jupiter, back here on Earth, scientists are just waiting. But forget the Hollywood version of this, okay? We're not getting some dramatic alien transmission over the radio. There is no giant, scary creature suddenly popping up on a glowing screen. The reality? It's just numbers. It's incredibly quiet, it's meticulous, and it requires some serious patient analysis. Section 3. The data arrives.
And then it starts. First, it's just a trickle of numbers. Thousands of pieces of information.
But then it scales up rapidly. Millions. An absolute, overwhelming wave of raw information flooding in.
These pieces of data, they come in fragment by fragment. Right off the bat, we get a radar reflection bouncing back from the ice.
Right on its heels, boom, a chemical signature.
Then, a magnetic measurement comes through, adding a whole new physical layer to the evidence we're building.
And wait, then we see a strange thermal feature. What on Earth, or rather what on Europa, is causing a heat anomaly out there in the freezing dark? Every new number forces a brand new question.
Then we zoom all the way down, literally down to the microscopic level, and scientists identify a single molecule.
And there's another molecule. Piece by painstaking piece, the invisible is finally becoming visible to us.
But here's the real magic. They don't stay as isolated data points. You combine the radar, the chemicals, the molecules, and suddenly they form a pattern, and then another pattern. All those seemingly random pieces of data slowly weave together into something we can actually recognize.
And slowly, Europa begins telling us what it is. Out of millions of numbers, through this quiet, methodical process of real scientific discovery, an entirely new world comes into focus. So the big question is, when 2030 rolls around and those patterns finally reveal Europa's true nature, will we be ready for what it tells us? Thank you so much for joining me on this explainer, and as always, keep looking up.
Welcome to the Explainer. Today we're setting our sights on Jupiter's icy moon, Europa. Now you probably already know it's got a hidden subsurface ocean, one that actually holds more liquid water than all of Earth's oceans combined. Europa has literally captured the imagination of astronomers for decades, but not for the reasons you might think. We're going to break down the actual science today and the massive philosophical shockwaves this little moon is sending through the scientific community. Get ready, because we're about to completely shift your perspective on the entire universe.
Chapter 20. The Real Fear. This is where things get genuinely mysterious.
Okay, let's dive into this. Why exactly is Europa so unsettling? You know, when we look out into the dark void of space, our human brains are kind of naturally wired to look for the familiar, right? Or, on the flip side, we look for monsters to fear. But when planetary scientists look at the data coming back from Europa, the chill that runs down their spines has absolutely nothing to do with little green men or sci-fi tropes. No, the unsettling nature of this moon is rooted in something way deeper, something that challenges the very foundation of how we define our place in the cosmos.
There's just this massive divide between pop culture and actual science here. On one side, you have the expectation. Scientists expect alien monsters. Hollywood has practically trained us to think that if there's fear associated with a frozen oceanic moon, well, it must be because there are giant, terrifying squids swimming beneath the ice. But then there's the reality. Europa forces us to confront a possibility that is much, much bigger. Maybe the real reason Europa is unsettling isn't because of monsters at all. It's because finding anything alive there forces us to confront a staggering, absolute, paradigm-shifting reality about the universe itself.
Section 2. The problem of one. Only one example.
To really grasp this reality, we have to bring things back home for a second. For centuries, Earth was our only example of a living world. I mean, really, think about that. Every single thing we know about biology, ecology, evolution, the fundamental mechanics of life itself, it's all been derived from this one single, lonely rock orbiting a remarkably average star. We've essentially been trying to figure out the rules of a giant cosmic game by only ever watching one single player.
1. It is hands down the most limiting number in science. Every biological theory we've ever constructed was built around one planet, one biosphere, one single example. Sure, we know life can exist because, well, we're here to observe it, but scientifically speaking, a sample size of 1 is practically useless when you're trying to figure out probabilities. If Earth is literally the only place life has ever sparked into existence, then life is this incredible miraculous anomaly, a fluke of staggering proportions. And honestly, that is the baseline we've been forced to operate from for our entire history.
Section 3. The Europa Catalyst. Beneath the ice.
But what if that baseline is just wrong? Imagine discovering that life began independently somewhere else. And we're not talking about Mars, which is right next door and, historically speaking, used to be quite a bit like Earth. And not on some Earth-like exoplanet in a distant, cozy habitable zone either, but inside a dark, freezing ocean trapped beneath an alien sheet of ice, constantly being bombarded by Jupiter's radiation. Europa breaks all the traditional rules. If we find microbes swimming around in that pitch-black subglacial ocean, it fundamentally destroys the idea that life needs a perfect, Earth-like sanctuary to get started.
Section 4. A second origin. Nature can repeat.
Now, what's really interesting about this concept is how an independent second origin reframes everything. It means the genesis of life is a process that nature can repeat, rather than a miracle unique to Earth. It means life isn't just some cosmic lottery ticket that was only drawn once in the history of time. Instead, it suggests that under the right chemical and thermodynamic conditions, even incredibly hostile ones, the universe is essentially hardwired to generate biology from chemistry. It becomes the standard feature of the cosmos, not just a random accident. So the crucial point here is the number 2. If life appeared independently twice, and not just anywhere, but twice in the exact same solar system, then the implications would be absolutely enormous. Finding life on Europa wouldn't just mean we have neighbors. It would mathematically prove that the barrier from non-living matter to living matter is incredibly low. If it happened twice around our one single sun, it fundamentally rewrites the equation for the rest of the cosmos. Section 5. The cosmic probability. Changing the landscape. To truly grasp the sheer scale we're dealing with here, let's zoom out. Start with the observable universe, which contains billions of galaxies. Within those galaxies, hundreds of billions of stars. And orbiting those stars are countless planets and moons. The math quickly becomes totally incomprehensible. Now, if life is a miracle, then maybe Earth is the only one among those trillions of worlds. But if life is a repeatable process, a process that happened on Earth and then happened again beneath the ice of Europa, well, those countless planets and moons suddenly look very, very different. And this brilliantly illustrates the main takeaway. One independent second origin of life would change the probability landscape of the universe. It's a massive statistical domino effect. We go from a universe where life might be a singular, lonely anomaly to a universe absolutely teeming with biological potential. A second data point changes the trajectory of a graph from a flat line into an exponential curve. Now, we need to be very precise with our conclusions here. Discovering life on Europa does not prove that intelligent aliens exist everywhere, or that there are sprawling galactic empires across the Milky Way. We aren't suddenly jumping into science fiction, but it does prove something incredibly important. It proves that biology is a natural, perhaps even inevitable consequence of the universe's physical laws. It shifts the entire philosophical foundation of humanity. Because ultimately, that potential discovery waiting in the dark waters of Europa leaves us with one staggering, unavoidable truth. Life can begin more than once. And if it happened twice in our own tiny cosmic backyard, where else is it waiting?
Welcome to this explainer. Imagine you're looking through a telescope right at Jupiter. You see this massive, swirling giant of a planet. But if you really squint, if you look closely around it, you'll spot these tiny, faint points of light just orbiting in the dark. Today, we're going to focus our attention on just one of those little points. Part 1. The frozen moon. When we actually zoom in on one of those specific points of light, we find Europa. And honestly, from Earth, it just looks like another totally ordinary moon. It's quiet. That's the very first impression Europa gives us. You don't see any massive weather systems churning on the outside. There are no chaotic surface disruptions at all. It just appears completely, eerily quiet. And it's frozen. I mean, it looks entirely frozen solid. Just a world locked in this permanent, absolutely unyielding state of deep freeze. Basically, it seems dead. Just a seemingly dead rock drifting endlessly out there in the dark void of space. But as we're learning, surfaces can completely deceive us. Which brings us to part 2, a hidden ocean. Because getting to the truth of this world really requires us to peel back that top layer of assumptions. The evidence we have now completely shatters that whole dead rock illusion. Turns out, beneath that surface, there is an ocean larger than anything we have here on Earth. I'm talking larger than all of Earth's oceans combined. It's likely been there for billions of years. And it's not frozen solid all the way down, because it's actively heated by the immense gravity of Jupiter, literally stretching and pulling at the moon's core. So you have this active liquid ocean surrounded by a rich mix of chemistry, totally hidden beneath kilometers of thick ice. Now, part 3, what hides in the dark? Because this kind of immense dynamic environment forces us to ask a really profound question. What actually happens in a massive body of liquid water that's heated by gravity and just left to stew in the pitch black for billions of years? Well, the possibilities kind of escalate step by step. First off, maybe it's nothing. Maybe it's just dark, empty water. Second, maybe there's a lot of complex chemistry happening, but chemistry that just never quite produced life. Or third, maybe there are microscopic organisms swimming around down there. And then there's the fourth option. Maybe, just maybe, there is something down there that would force humanity to rewrite the entire story of life itself. Right now, we genuinely don't know. Which leads us to part 4. The Europa Clipper mission. Because the amazing thing is, we aren't just sitting around guessing anymore. The answer to this cosmic mystery is quite literally traveling through space toward us right now. The Europa Clipper spacecraft launched back in 2024. As we speak, it is in transit, making that long journey. And in the year 2030, it is scheduled to finally reach the Jupiter system and begin its close flybys right past Europa. And when it finally arrives, everything changes. We're going to move from the past, where we were just looking with our eyes from afar at this seemingly quiet, frozen moon, straight into the future. For the very first time, we're going to look with precise instruments. We're going to rely on rigorous measurements and concrete evidence to actually see what's happening in the world beneath that ice. Part 5, a new question. Because whatever Europa ultimately tells us through all this incoming data, one fundamental thing about human perspective will have already changed forever. You see, the core question that has driven space exploration for decades will instantly evolve. We're going to move past just asking, could there be life beyond Earth, to an entirely different, much bigger paradigm. We'll be asking, how many places could life exist? Think about that. How many places could life exist? I really want to let the existential weight of that new question sink in for a second. If a seemingly dead, completely frozen moon can secretly hide an ancient, active ocean, man, what else is out there? Because honestly, perhaps the most frightening possibility isn't just what might be hiding beneath Europa's ice. Perhaps it's the realization that the universe has been making oceans exactly like this one for billions and billions of years, and we are only just now beginning to look. We are just now opening our eyes to the true nature of the cosmos. Thanks for joining me for this explainer. Unspoken truth, the